welcome everyone for the today's talk by Piotr Indyk. I have Thomas Hollenstein is here with me, helping to run this operation. Behind the scenes, we also have, as usual, Gautam Kamat, Clement Canon, Anindya De, and Thomas Vidik. Then before I go on, let's go around the table. I see lots of new faces, so Thomas, maybe we can quickly go around the table.
Okay, thank you, Audit. Yes, so we have a group from CUNY here for the first time, I think. Arnaud Sbarnoy is here for them. We have Clement Canon here from Columbia. Hello, Clement. We have Davai Huang from the University of Michigan. Hello, Michigan. Then we have Joop Priet. This is complicated, from CWI. Hello, CWI. We have from Caltech, Piyush Srivastava. Hello, Caltech. We have a group from UCSD, which is organized by Shachar Lovet. Unfortunately, we don't have picture right now, but okay. We have a group from New York University, so led by Shravas Rao. Hey, hello, New York. We have a group from Indiana University in Bloomington, led by Hao Yu. Hello, Indiana. And that's everyone who's here so far.
Okay, thank you, Thomas. So before we go on, let me just mention, so the next talk in 2 weeks is going to be by Virginia Williams from Stanford. That's going to be the last talk of this fall. And also, we need your help, so let us know if you hear a good talk and you think it would be a good match for TCS Plus. Let us know. There is a forum on our website where you can let us know about that. So, you know, if ever you hear of a good talk, please let us know and we'll add it to the spring schedule. Also, as usual, please ask questions, especially true because Piotr can't see you. He only has one monitor, so please interrupt with questions to make this more fun, more interactive. So finally, I'm happy to introduce Piotr Indyk. Piotr joined MIT in 2000 after completing a PhD in Stanford. Piotr won lots of awards, Career Award, the Sloan Foundation Fellowship, Packard Foundation Fellowship, Simon's Investigator 2 years ago. His work was chosen by Technology Review as one of the emerging technologies that will change the world. We'll hear about some of that today. His main interest is in algorithms for high-dimensional geometric problems, sublinear time algorithms, streaming algorithms, locality-sensitive hashing, and today he'll tell us about fast algorithms for structured sparsity. So thank you, Piotr, and please go ahead.
All right, thanks Odette and Thomas for introductions and for preparing this talk. Yes, I'm new to this medium, and as Odette mentioned, I forgot to plug in the other screen, so I cannot actually see who I cannot see you guys. So you know, feel free to just you know, speak up whenever you have any questions, right? Because the more interactive we can make it, the better. All right, so this talk is about fast algorithms for structure sparsity. So this will be an overview of a line of research that several people, including myself, have been doing over the last few years. Most of this work is done jointly with my former postdoc, Chin Hegde, and my current student, Ludwig Schmidt, and some of the more applied work is done by a group from Shell. All right, so the topic of the talk is fast algorithm for structure sparsity. So let's start from the basics, namely the sparsity. So over the last few decades, I guess by now, it has been observed that lots of data out there has this nice property of being sparse. So by data, you know, for the purpose of this talk, I would just mean some vectors in a high-dimensional space, say images or some other audio files or things like that. So what I mean by sparse, well, sparse means that if you look at a vector, right, or a signal, like for example this image, right, n-dimensional image, then most of the information in this image is concentrated in only a small number of coefficients, right? So in particular, you see that most of this image is black, which means that most of the pixels are 0 or very close to 0. And only a small number of pixels have a high intensity, and this is where the information is hiding. Okay, so that's what I mean by sparse. And over the last few decades, it has been people realize that this is a very common phenomenon. So it very often happens that data that people encounter in practice is sparse, right? So this is a classic example. This is a astronomical image, right? The sky is black. You have only very few stars. Here is another example. This is a slice of a rock, and what you see here, these stripes correspond to faults in the rock structure. Okay, so again, you can see that most of the rock is not very interesting, right? Faults exist, but they are rather sparse, right? And also they correspond, on this image, they correspond to the pixels with the highest intensity. So these are some of the examples of sparse signals or sparse data. Now there are others, and in particular, in many situations, when you just get your signal or an image, the image might not be sparse as it is. However, it's very easy to convert it to a sparse representation, right? So, for example, if you look at this image, right, it's an image, of some landscape. It doesn't appear to be sparse. However, what one can do is one can apply a linear transform, basically change of basis, and after applying this change of basis, in particular, here we apply the wavelet transform. You get an equivalent representation of your data, which is now sparse. Right, so what you see here, I will not formally define what a wavelet transform is. However, you can roughly see what is happening, right? That each image is replicated, right? And there are several levels, right? This is one level, this is second level, this is a third level. And on each level, roughly speaking, a wavelet transform, extracts edge information from the original image, right? So after you perform this transformation, now if you look at this image, you can see that this data is relatively sparse, right? The diffraction of pixels of high intensity is small, and and therefore, you can actually observe sparsity. So, so these are just some of the situations or some of the applications where you see sparse data. And over the last few decades, people realize that if your data is sparse, then lots of good things can be done, right? Lots of good things happen because of sparsity. So here are some of the applications or some of the benefits of sparsity. Well, for starters, if your data is sparse, you can compress it easily, right? Because you just need to store the small number of important coefficients, and you can forget about everything else. So this is, in fact, how many compression standards operate these days, like JPEG, JPEG 2000, or MPEG. All of them take your image or video and transform it into an appropriate basis, and then just extract the large coefficients. Right, so this is one classic application of sparsity. Another classic application is denoising. So here the idea is that often the sparse component is actually where the information is, and everything else is pretty much noise. Right. So if you look back at this space image, right, this is where the information is. The rest is just background, right? So you could just completely remove the background, and in this way you denoise or enhance the image. So that's the idea behind sparsity-based denoising, right? You just keep the sparse component because that's where the information is, and you remove the dense component, which is basically everything else, which is often noise. And there are many other applications of sparsity. It's something which is very useful in machine learning. And over the last decade, sparsity found another important applications to compressive sensing. I will not talk about compressive sensing right now. I'll define it later in this talk. But the basic idea is that it's a framework that lets you recover your data from small number of measurements, and the sparsity of the data is crucial for this approach, right? So basically, this whole approach is based on the assumption that the data you are dealing with is sparse. Okay, so these are the some of the applications of sparsity that people discovered and developed over the last few decades. Okay, now so hopefully by now you see that using sparsity you can do lots of good things. Now the main what this talk is about is that you can actually do better. If instead of considering just the basic sparsity, you actually look at the structure beyond the basic sparsity. Okay, so I will define what I mean formally in a moment, but here is the basic idea. Okay, so all of these are examples of signals that we have seen so far. They are sparse, right? At least if represented in an appropriate basis. However, they have more structure than just sparsity, right? So, for example, let's go again to the image, right? The Hubble image, right, of stars. So if you look at this image, you see that the large coefficients are not distributed, completely uniformly at random over the whole image, but in fact they are highly concentrated, right? They are clustered because those high-intensity pixels come from stars, and the image has only 3 or 4 stars. Okay, so this means that this image has a structure that goes beyond the basic sparsity. Right? It's not just that there's a small number of large coefficients, but these large coefficients are actually clustered together. Okay, so this is what I mean by additional structure. And similarly, if you look at this image, you can also see that this image, right, the wave representation of the original image, in fact, consists of sub-images which are quite close to each other, right? So in particular, if you see, this image and this image, you pretty much see that whenever there is some high-intensity pixel here, there's also the corresponding pixel in this smaller image also has a high intensity, right? So again, the positions of these large coefficients are correlated, and this is another example of structure that we can exploit. And last but not least, if you look at this, seismic image here, as I mentioned, what we are really interested in are faults. Faults are strips, right? So, they also have structure, right? They basically form this contiguous, what shall I call it, lines in the image, right? So again, these high-intensity coefficients are not in arbitrary places, but they are correlated. So that's this correlation, represent a secondary and additional structure of sparsity, and basically the goal of this talk is to give an overview of how to model such structure and how the structure can be useful, for a variety of applications. So in particular, this is the plan for today. So the first things first, I will define formally what I mean by structure sparsity, and I'll present one of the most popular models for representing or defining such sparsity. And I will give a few examples of particular models that can be formulated in this way. In particular, I mentioned block sparsity, tree sparsity, and cluster sparsity. I probably won't have time for a constraint EMD model, but it's also another example. And so in this way, we'll see, what are the examples of structures that one can exploit. And then in the second part of this talk, I will describe efficient algorithms, right? So given a signal which has some structured sparsity, how do you extract this structure from the image? And in particular, how do you do it quickly? Okay. And in the last few minutes, I will describe one application of these tools to compressive sensing, right? Particularly, I will show how you can get compressive sensing with a better performance if you, in addition to sparsity, also use the structure of the image. Okay, so that's the plan. Now it's probably a good time to ask if there are any questions so far.
I don't see any, so we can go on.
There are no questions? All right, everything is crystal clear so far. Okay, let's hope it will stay this way. Okay. All right, so first things first, how do we model structured sparsity? So in fact, there are several ways of doing it. In this talk, I'll focus on the model that, to the best of my knowledge, was first introduced by Blumenthal and Davis in 2009. But the specific models have been popular before. This is just a general formulation. So the idea of this model is very simple. Basically, we specify the structure by specifying the list of allowable sparsity patterns. Okay, so the model is simply a family of sets of coordinates, where each set has at most k coordinates. And these are basically the allowable, these are the patterns that we allow in the model. Okay, so in particular, once we specify this set of subsets, then this set corresponds to a family of signals, right, of vectors in an n-dimensional space. And this family is defined in this way, right? So it's a set of all n-dimensional vectors such that the support of the vectors, the support is the set of non-zero coefficients, has to be included in one of the allowable sets. Okay, so this is the way we define the class of allowable sparsity patterns and the corresponding class of sparse signals. Okay, so let's see an example. Okay. So what you see here on the left is the set of all sparsity patterns corresponding to a sparsity of 2. Right, so this is basically n choose 2 different patterns that two sparse vectors can have. Right, you know, you have dimension is 5, right, and you select all tuples. Okay, so this is a model without any structure. Right, here we just assume sparsity of 2. Now, in order to specify the structured model, we have to select a subset of the sparsity patterns, right? And this is an example. Okay, so here what you see is we selected only the patterns such that the two coefficients are next to each other. Okay, so we have only 4 different patterns. Right. So this model, or this set of sparsity patterns models situations where the large coefficients occur next to each other. Right, which is, you know, basically you only take the sparsity patterns where the non-zero coefficients are neighbors. Okay. So this is how we can model the sparsity. Okay. Any questions? Okay, so let's see a few classic examples of models that fall into this framework. So perhaps the simplest one is the so-called block sparsity, which intuitively models the fact that in many signals, large coefficients are clustered together. Okay, so in the block sparsity model, we take our signal and we divide it into blocks, right? In this case, each block has length 3. So here we have 3 blocks, each of length 3. And we only allow sparsity patterns which contain coefficients in at most L blocks, right? So here L is 1, which means that we only allow sparsity patterns that have non-zero coefficients in only one block, right? So we can have non-zero coefficients here, or non-zero coefficients here, or non-zero coefficients here, but we cannot have, say, non-zero coefficient here and here. Right? This is not allowed by our model. And in general, in the block sparsity, we allow sparsity patterns that are union of at most L blocks, right? And for any value of L and the value of B, the value of L and the value of B specify the sparsity. Sparsity is K is equal to B times L, right? Because we can have at most L blocks switched on, and each block corresponds to B coefficients. Okay, so this is one example model of sparsity, and it's very simple, but it's actually very useful. Right, so you can generalize it easily to 2 dimensions, and then it's a way to model, for example, astronomical images like that. Right, because if we split this model into, if we split this image into blocks, then given that each star is a blob, this blob will overlap with only small number of blocks, which means that if we set the number of blocks, to something like, say 3 times 4, then in this way we'll be able to capture 3 stars, right? So in other words, block sparsity is a model that can exploit a spatial correlation between the large coefficients. Okay, does this make sense?
Yes, this makes a lot of sense, but we do actually have a question from a little bit back. So it's asked whether it's necessary for M to always be explicitly given, or whether you can have, say, the sets of K tuples which are defined as the zeros of some family of polynomials, or some more implicit definition.
I see. Right. So right now, M is just. So actually, it's a very good question, and I will talk more about it in a few slides. In this particular, right now it's just a definition, right? So it's a mathematical notion. But you are very much right that in most situations, this set is actually very large, right? Because it can be it could be exponential in K. So we'll need to have some implicit representation of those sets, and in fact, I will define exactly what we need in a moment, right? But yes, in general, we never actually write down explicitly all of the sets because there are just too many of them, and we want fast algorithm, right? So we definitely have certain implicit. We'll have to model this implicitly. And I will describe how in a few slides. Okay. Any other questions? Okay. So this is one example of a model. So let's see another. So another is a little bit more funky, but it's also very useful. So in this model, the coefficients are associated with nodes in a full TRE tree. Okay, so basically you can think that each of these nodes in a full TRE tree corresponds to a coefficients in the signal. Okay, here in this picture T is 2, so we just have a full binary tree. Okay. And so that's the set of coefficients. Now, what's the model? Well, in this model, the sparsity patterns that we allow correspond to all rooted subtrees of size at most K. Okay, so we take all subtrees which are rooted, right? So they have to contain the root, and any subtree which has at most K elements corresponds to a set of coefficients, and these are all such trees correspond to our sparsity model. Okay, so you might wonder where this model is coming from. Well, it turns out that it's actually a very natural way to model structure of the wavelet coefficients, right? So again, here you have an example of an image after applying the wavelet transform, and as I mentioned earlier, this is the structure of this set of coefficients is like multi-level, right? You have the top level, you have the next level, and so on. And what people empirically observed is that whenever one of the low pixels in the lowest level has a large value, the chances are that its parent on the higher level also has a large value as well. Right, so this motivates these sparsity patterns. Right, whenever some node is in, that also all of its ancestors are in as well, because they are likely large. Okay, so that's the reason why we define the tree sparsity in this way. Okay. So this is another model, and the last model that I will define the talk, in fact, it subsumes all of the previous models. In this model, the nodes of the coefficients of the signal are associated with nodes in some arbitrary graph, right? So the graph is given to us, and the sparsity patterns correspond to all subgraphs of our original graph, which contain at most G connected components. Okay, so G is a parameter, sparsity K is parameter, the graph is also a parameter. Okay, so as you can see, this is a very general model. In particular, it essentially generalizes the previous model, right, the tree sparsity, for the case where you have only one connected component and the underlying graph is a tree. Right, so in this model, you have arbitrary graph and you have arbitrary number of connected components, or more than one. And this model is useful in many applications. In particular, it models the seismic images that I mentioned earlier. Right, because in seismic images, you want to extract information about seismic faults. And the seismic faults are connected components, or maybe there are a few of them. Here there is just one, right? And the bright pixels, they form a connected components in the underlying grid graph. Okay, so these are the examples of a graph sparsity that we'll focus on. Sparsity models that we'll cover in this talk, and there are many others, but I think that 3 is enough for now. All right, any questions? All right, so so far I just defined the models. But as the earlier question indicates, we need more than models, right? Because model is just a specification of the set of allowable patterns, right? But at the end of the day, we need algorithms which are, somehow help us extract this sparsity structure from the data. So this is. In order to extract this sparsity structure, what we need is something which is called a model projection or model projection oracle, and this is basically how we treat those models empirically, computationally. And essentially, what a model projection oracle does, it's given the signal, it returns the closest signal in the model. Okay. So formally, what we need this oracle to do is we give it a signal, x, right, n-dimensional vector, and the oracle finds the closest signal from the model, the closest to the input x, right? So it's a nearest neighbor in the space defined by the sparsity pattern. Okay, so this is how we deal with this sparsity models empirically, right? By defining and implementing an appropriate model projection oracle, right? So now, if you define your sparsity patterns as roots of some polynomial, it's fine, as long as given a signal x, you can quickly find the closest signal in your model, right? If you can do it, then you can use this framework. All right. So for example, in this particular case, if we are dealing with the block sparsity, with the graph sparsity, and if we are given this image, then the goal of the model projection oracle is to basically extract these coefficients. Right, so the closest, the best omega, right, in this definition would basically correspond to something like this. Okay. And so that's an example of the of what we want to do.
Okay, so Clement has another question here. So
sure.
You choose the L2 norm here for the minimization in the argmin problem. Are there other norms possible or?
Right. Yes, that's a very good question. I chose the L2 just for simplicity, but you could use L1 or other norms, transportation norms, and all of these things have been studied. Yes. So here I'm just using L2 for simplicity, but there's nothing in stone, right? You can vary it if you and people study variants as well. Yeah. Good. Any other questions? All right. So let's see what is known about model projection oracles. And there is a piece of good news and a piece of bad news. Okay, so let's start from the piece of the good news first. Well, the good news is that several important models actually do have projection oracles which have a polynomial time complexity. Okay, so perhaps the simplest case again is the block sparsity. Block sparsity is very simple. Basically, all you need to do, you need to process each block separately, compute the L2 norm of each block, and pick up L blocks with the highest L2 norm, right? And this is the best approximation that fits the model. Okay, so this is a very simple, procedure. You can have the model projection oracle for block sparsity that runs in linear time, right? So that's very nice. Now, tree sparsity is a little bit more tricky, but as I will describe in a few slides, in fact, there is a way to find the best tree sparse signal in time, which is well, it's not linear; it's rectangular. Right, so it's n times k, where n is the size of the signal and k is the sparsity parameter. Okay, so it's not linear; it takes a superlinear time, but it's certainly polynomial. Okay, so these are the good news. Now there are also bad news, and they are twofold. So first of all, just having polynomial time in many applications is not enough. Right, so if you look at this running time. And if you think about what it would be for a very typical example, right? Let's say that you want to extract a structure of an image with 10 megapixels, and typically the sparsity natural images is a few percent of the number of pixels, right? So let's say 5%, right? So if n is 10 million and k is 5% of 10 million, then n times k, if I got it right, is well, whatever it is, it's a pretty large number, right? So it can take hours or maybe in some situations even days to actually process such images, even though you have a polynomial time algorithm. And the second piece of bad news is that for some models, for example, for graph sparsity, the exact model projection is corresponds to an NP-hard problem. Right, so basically, you pretty much cannot solve it, in any reasonable time. All right, so what do we do in situations like that? Well, what we'll do is what we typically do when we are faced with hard or intractable problems, which is we try to solve them approximately. And by allowing approximation, we're able to see how to solve this problem much faster. Okay, so basically, instead of trying to find the exact solution to this optimization problem, we'll try to find an approximate solution, and then we'll show that A, this can be done much faster, and B, approximation suffices in many applications. However, it turns out that defining what we mean by approximation is actually not so immediate, because there are, in fact, at least two ways of doing it. Okay, so perhaps the more natural one is something that is often called the tail approximation, which essentially takes this objective function and puts some approximation factor in front of it. Okay, so instead of trying to find the exact minimum, we are happy with something which is within factor CT of the minimum. Okay, so this is a approximate nearest neighbor, right, in the space of a allowable signal. So that's one way of doing it, but there is an alternative way of defining approximation, which is to think about this problem not as a trying to minimize the error, but as trying to maximize the amount of information extracted from the image, right? So we can basically think about this minimization problem as trying to maximize the norm of the projection of x on omega. And this is equivalent formulation in the exact case, right? Now, if we relax it, we get an approximate maximization problem where the goal is to find some set omega such that the projection of x on omega is within some constant factor away from the largest possible projection. Okay, and this formulation is often called the head approximation, right? Because head is basically the signal that we extract, and the tail is everything else, right? So here we try to minimize the norm of the tail, and here we try to maximize the norm of the head, right? And again, in the exact case where CT and CH are equal to 1, these problems are equivalent, but they could be very different in the approximate case. Right, so this is kind of reminiscent of say independent set and a vertex cover, right? That in the exact case they're equivalent, but once you put approximation factors, their behavior is very different. Okay, so these are two ways that we can define approximation. Now, which one to choose? It actually really depends on the application. Tail approximation works great if the tail is small. In particular, if this is 0, then this is 0. So it means that we have an exact recovery. But in many situations, we actually don't have such a small error. For example, in iterative algorithms, the error starts to be large, and then we decrease it as the more and more iterations proceed. And in situations like that, it's useful to have the head approximation, because head approximations extract some information from the signal, even if the error is very large. Right? So if there are say 2 meaningful coordinates in the signal, then maybe the head approximation is going to recover only 1 meaningful coordinate, but still it's better than nothing. Right? So depending on the applications, either tail or head approximation is appropriate. In fact, for the compressive scaling application that I will describe later in this talk, we actually need both, right? So we actually need potentially two different algorithms, one with a tail guarantee, one with the head guarantee, and once we have both, you can actually run the algorithms, right? And we don't know whether you can do with only one of them. And last but not least, I should mention that in general, these model projection oracles actually might not report k-sparse vectors or vectors that are in the model, but in all examples that we see in the stock, they always report something. I mean, it might not be k-sparse, but it's always order of k-sparse, right? And they also correspond to the model, right? So one can think about it as a bi-criterion approximation, right? We approximate both on the error and also on the amount of sparsity. Okay. Okay. So this is perhaps the most important definition in the stock. So if there are any questions, go ahead. No questions. Okay. Excellent. Cool. All right. So well, so now that we defined this notion of approximation, let's see what we can do with it. So in the rest of the talk, I will describe algorithms, 3 kinds of algorithms, 2 algorithms for the tree sparsity, and in particular, we'll see the exact algorithm. It's a very cute dynamic programming-based algorithm. It runs in k times n time. And then we'll see how we can get approximate head and tail oracles which run in a near linear time. right? So the benefit of this algorithm as opposed to this is when n and k is large, this algorithm is much faster than this one. And the last algorithm that I will mention corresponds to graph sparsity, and in particular, we'll see how to get an algorithm with a running time again n polylog n, and it's based on the Gemans-Williamson algorithm for the price collecting Steiner tree. And after I describe this algorithm, I will present a few applications, and then we'll conclude. But by the way, what time should I finish?
We usually try to finish around 2, but you can take a bit longer if you need.
Okay.
That's great.
Yeah,
we can also stay longer and take a short break and continue after the break. It's up to you.
Sure. Okay. Yeah, I think that 2 p.m. is fine. So basically, like 20 more minutes, right? Yeah, that should be fine.
So I have a stupid question now. How should I think of these algorithms? Is it useful for something, or just a tool to build other algorithms?
Oh, I see. So these algorithms can be directly useful for something. So that there are situations where, let's see, for example, so in situations like this, the algorithms are directly useful for extracting the structure of the faults. Right. So in fact, the joint work with people from Shell is exactly about using structure sparsity for extracting faults from seismic images. Right. So and there are many other situations like that. Right? So basically, this is the input and this is the output. Right. So the algorithms are useful in itself. Now, in many other situations, the algorithms are useful as building blocks, and we are also going to see a situation where this is the case, basically for the compressive sensing application. Right. So there, this model projection oracles are useful as subroutines to get sparse recovery algorithms with better performance than the algorithms that don't use the structure of the data. And we'll see example of it as well.
Thanks.
Sure. All right. So let's start from the tree sparsity. Right. So again, remember that the goal is to find each coefficient as a node in the tree. And what we want is to find the rooted subtree of size k, which maximizes the norm of the extracted of the projection on a tree, or alternatively minimizes the stuff that is not selected, right? And depending on which formulation we choose, right, then approximate definition are slightly different. So this problem has been studied for quite a while, and the exact algorithms has been known for some time. There were also quite a few heuristic algorithms, and they don't necessarily have guarantees that can be described in this way, although the algorithm of Donoho actually comes pretty close. And we use this algorithm in our approximate tail oracle. So in the work with Chinmay Hegde and Ludwig Schmidt, we managed to develop a near linear time algorithm for both formulations, and in both cases they run in time n polylog n. Okay, so let's see how these things work. But actually, before we see the approximate algorithm, let's see how the exact algorithm works. It's actually
quickly ask one question. So we have one. There is one. Are there any lower bounds for approximation, or do we know whether these approximation factors you achieve are optimal, or can you say anything about that?
There are no known lower bounds on the approximation factors. The part of the issue is that here everything is in P, right? So you'd have to use some problems which are conjectured to be things like from like tree-sum or similar problems, right? That are conjectured to require at least say quadratic time, right? To argue any hardness, right? So you cannot use NP hardness theory because everything here is in P, right? Now the situation is a little different for graph sparsity because there we actually have NP hard problems. So as you'll see, then the answers will be different, right? But I will get back to this question when we get to graph sparsity. Yeah. Yeah, in particular, I would love to know whether nk is tight under some natural assumptions for tree sparsity, right? So I don't know, and it would be nice to reduce tree sum or other problems as conjecture to be hard to this problem, right? To get some evidence of hardness, but I don't know how to do it. Okay, so let's see how to get the algorithm with a running time n times k. It's actually a very cute dynamic program. All right, so the dynamic program uses or builds a table, right? Opt t comma I. T stands for sparsity, and I stands for the node, right? And this is basically the best solution that you can get if you are rooted in the node I and use only tree of sparsity t. Okay. So once you define it, computing it is relatively, straightforward. It's a simple exercise. Basically, the optimum, to compute the optimum, I guess it's not error, it's the opposite of error, right? So information, right? Well, first of all, you lose one coefficient on the node I, right? So this is basically what you get if you include this coefficient. And then you have to figure out, what to do on the left and what to do on the right, right? So you can have, you can use up to t coefficients on the left and up to t coefficients on the right, right? But they have to sum up to t minus 1. So just take all the combinations, right? And the best combinations is the right solution. Right, so this is a very nice example of a dynamic programming problem. In fact, I often give it in my algorithms course. So I hope that none of my undergraduate students are watching this right now, because I would love to give this problem somewhere in the PSET. Okay, anyway. So that's basically the whole algorithm. Right? Now, how to analyze it? It's actually it's a very simple observation, but it's nice, which is that naive analysis of this algorithm would suggest that this algorithm uses n times k space, right? Because t ranges up to k and I ranges up to n, right? So the upper one will be n times k. But in fact, this is an overestimation. Right? And the reason for that is that if you look at the coefficients at the lowest level, then those coefficients, in particular the leaves, they don't have any subtrees, right? Which means that the only sensible sparsity budget for those coefficients is either 0 or 1, right? So, and similarly, if you go up, right, from level 1 to level 2, level 3, and so on, see that at the lowest level, the allowable sparsity budget is only at most 2 to the power of L, right? At the same time, the number of nodes at level L is n over 2 to the L, which means that the total space used per each level is n, and there are log n levels, which means that the total space is only n times log n, right? As opposed to n times k, which you would just use by upper bounding each of these individual components. So this means that the algorithm uses n log n space, and this immediately gives us an upper bound on time, which is nk log n, because we have n log n things to compute, and this loop takes the time at most k. But by slightly more careful analysis, you can observe that in fact the time is only n times k, right? And this is the best known running time for the exact version of this problem. All right, so in our case, we don't try to improve the exact version, but we improve the approximate problem. So what's the idea? Well, for the tail oracle, we use essentially Lagrange relaxation of the problem, which means that instead of constraining the sparsity to be at most k, we just penalize the objective function for each new coefficient that the algorithm takes. right? And after we do it, we use the different dynamic program due to Donoho, and then do some Pareto curve analysis, and that's how we get algorithm approximation, constant approximation algorithm. Now, for the head oracle, the idea is a little bit different, and essentially the idea is to use to combine dynamic program with a form of a greedy algorithm. Okay, so let's see how it works. Okay, there is a typo here, and I apologize for that. Probably best if I fix it. Not confusing. Right, so basically what we want is we want to extract as much information as possible from the tree, right? So we want to pick up a tree which are, total mass of the coefficients in the tree is as large as possible. So the way we do it is as follows. So first we observe that the optimal tree, or any tree in general, can be decomposed into smaller trees. Each tree is at most log n, and all of these trees are disjoint. Okay, so for example, this is how we could decompose our optimal tree. And the algorithm proceeds greedily, and essentially we try to recover this optimal or near optimal tree by picking one small subtree at a time. Okay, so in particular, we compute optimally the best subtree of size log n, right? We add it to our solution, and then we pick up the next subtree, and so on, right? So here is this approach in more detail. And at the end, we get some sort of approximation, right? So more specifically, during the preprocessing, we run the dynamic programming, the exact dynamic program, as I described earlier, for the exact tree sparsity, but we only set the sparsity to log n, right? So it only deals with trees of size up to log n, and therefore it runs in n log n time. And after we do it, we pick the best subtree, right? It could be, say, this tree. And then we perform a loop, right? K log n times. In each step, we select the next best log n sparse tree. Once we select this tree, we zero out the corresponding coefficients, right? Because we already picked it up, so picking up the same coefficient again doesn't give us anything, right? So we set these things to 0. And then we update the data structure that we obtained for dynamic program, so that the dynamic program takes into account the fact that these coefficients are now set to 0. Okay, so we do it once, we do it twice, and so on. And after k over log n times, we get some sort of approximation to the optimum tree. Right, and the reason why it works in near linear time is because updating the data structure can be done efficiently, because we only at each step we zero out only log n coefficients, and which results in the information in the dynamic program being propagated up the tree, but there are only log n levels. Right, so each coefficient which is zeroed out only results in a logarithmic number of changes, and therefore all of this update can be done in polylogarithmic time. Right, and since we perform everything k over log n time, it means that this part runs in k polylog n time, and that this part runs in n log n time, which gives us a near linear time algorithm.
Piotr?
Yes?
Are we guaranteed that the output is a tree, or it can be any k-sparse set?
Right. So as I described, it could be any set or any collection of at k over log n sparse trees. However, what we can do is that after we get those trees, we can actually, using very little extra coefficients, we can connect all of them into one single tree. And by changing the numbers here slightly, in particular, instead of having k over log n, we take k log n over 10. We can even ensure that the sparsity is also at most k, right, while maintaining a constant factor here. So for this algorithm, we can actually ensure that the output is a rooted tree of size at most k. Yeah, but it's not always true for all of the algorithms.
Right. And am I guessing correctly that CH, that the constant there, is 1?
Oh, the constant that we get is not 1. No, so it's not an exact algorithm. There's a trade-off between the number of times you repeat and the approximation factor, right? It's a little bit like max coverage. In max coverage, right? If you want to output exactly, the maximum. If you want to pick up k sets which cover the largest amount, the largest part of your universe, right? If you pick exactly k, you get a 1/epsilon approximation. If you pick more than k, you can get a better approximation factor, right? So it's a similar trade-off in this case.
Okay. So should I think of it as 1 plus log n over k? Or?
So CH here, you can think about as 0.1. Okay, so there's the same problem that happened earlier. I really apologize for that. Does it make more sense right now?
Yeah, this is head approximation.
Yeah,
it's clear, yeah.
yeah, head approximation. Yeah, so basically you want to pick up as much mass as possible, right? So you don't get the optimum, but you get, say, within, 10% of the optimum.
Okay, thanks.
Yeah. All right. Okay, so here is that's basically how our algorithm works. And that concludes the tree sparsity. Now for graph sparsity, I already mentioned what it is, right? The model consists of a bunch of components, G components that use a total of k coefficients. Now that problem is NP hard, and it's basically not difficult to see it by reduction from a Steiner tree. So we need the approximation algorithm to get anything that runs in finite time. And here our approach is, again, as before, to use a Lagrangian relaxation, right? So instead of constraining the number of selected coefficients to be k, we just penalize each coefficient we pick up. And after we do it, we get something that it's essentially a price collecting Steiner tree problem, right? Because we want to, find some subtree, right? Here we just assumed for simplicity that we have only one connected component. So we want to find a subtree, and we we pay for each element in the subtree, and we also paid for prizes that we did not collect, right? So this is the stuff that we missed. Right, so this is basically price collecting Steiner tree problem, and there is a very good two-approximation algorithm due to Gemmas-Williamson, which has a near linear time implementation due to Cole et al. So basically what we did in our paper is we slightly improved the runtime, and we showed how this can be used to solve both the head and tail formulation for the weighted graph sparsity model. And funny enough, this combination enabled us to solve most of the structured sparsity problems considered in the literature in a way which is both measurement optimal and very efficient. Okay, so and this is in part because this algorithm works very well in practice, and that there is a good implementation. And in part because this graph sparsity model is very general, which means that we can apply it to many different sparsity models. Okay. All right. So let me. So this concludes the description of the algorithm. So in the last few minutes, let me describe application, and in particular, the applications that I will describe are to compressive sensing. So here is a quick primer what compressive sensing is. We have some high-dimensional vectors, for example, images. What we want is compress those images by applying linear measurements. right? So we have our X, we want to hit it with a matrix A to get a measurement vector or a sketch of the vector X. And after we get this measurement vector, with possibly some noise, what we want is to recover an approximation, right? So X is the truth, but what we find is a X star, and the idea is that the error should be small, right? So in particular, if the truth is K-sparse, right, then that means that it actually has only K not zero coefficients. Then our goal is to find some approximation which is basically pretty close to the original signal. You know, the only difference is this noise, right, that comes from the measurements. But there are other formulations of this problem, but this is the most general one. All right, so so what do we want from the compressive sensing methods? Well, we want good compression, right? So we want to have a good recovery from as few measurements as possible, right? So this sketch vector, we want this to be as small as short as possible, and of course we want to do it fast, right? So given this, we want to get approximation to this as quickly as possible. So there has been lots of research over the last 10 years about this problem. In particular, it's known that you can get a K-sparse approximation from K log n, or log n over K measurements. And it's also known that you can do it in close to linear time. In fact, there are some algorithms which do it in time proportional to the sparsity as opposed to signal. So this is pretty good. Now this here has this annoying logarithmic factor, and unfortunately it's known that for general sparsity this factor has to be there, right? So one can prove that this bound is tight, okay? And it's unfortunate because in many applications this logarithmic factor actually changes the number of measurements by order of magnitude, right? So people spend lots of time trying to reduce the number of measurements. And one way of doing it is to exactly use the structure of the sparsity. So this leads to this so-called model-based compressive sensing, which I will not describe in any level of detail, but let me just mention that for the types of models that we discussed, like tree-sparsity and block sparsity, you can actually get rid of this logarithmic factor, right? So you can perform solve exactly the same problem as before for the structure sparsity, but using only order of K measurements. Right, and this is because you know, such signals are simpler, right? So you need fewer measurements to recover them. The first paper to do it for a general class of signals was a paper to Baraniuk et al. And they showed how to perform this recovery, assuming that you have an exact model projection. Okay, so. You know, so for models where exact model projection oracle is feasible, you can apply these techniques. But in cases where the model projections can be hard or just polynomial with a large exponent, these algorithms were too slow. Right, so basically, in a recent paper with Chin, Hegde, and Ludwig Schmidt, we know that one can take their framework and replace the exact model projection with approximation. And as I mentioned earlier, you have to use two notions of approximation simultaneously, right? So you have to have one oracle for tail approximation and one oracle for head approximation. But once you have both of them, you can just plug these approximations directly in the model, and you get a faster algorithm with also exactly the same performance. Okay. So, so let me very quickly show how those algorithms work in practice. So these are experimental results from our ICML paper. So what you see here are three examples of relatively sparse images, right? One, an image where the non-zero coefficients correspond to some silhouettes of, I guess, humans. Another image that corresponds to so-called the angiogram, right? So, you know, these are just like tentacles that occur in human body. And another example, which I'm not going to claim it's a realistic example, but, you know, I guess you can see what it is, right? It's ICML written by hand. And below, what you see is the performance of several different algorithms. Our is in blue. And in particular, we measure the probability of correct recovery as a function of the number of measurements taken, right? So here is the number of measurements, and here is the probability of correct recovery. So if you look at these graphs, right, you can see that our algorithm is doing pretty well, right? So in particular, the probability of recovery hits 1, pretty quickly, right, for a relatively small number of measurements. It's better than all the other algorithms for this and for this case. For this case, this algorithm here, which is the structure OMP, which is a different way to approach structure sparsity, is a better. However, this algorithm doesn't work as well for sparsity patterns, which are not blobs, right? So here, when you see that sparsity patterns which are, thin, especially here, right?
Can I?
Excuse me. Yes.
Yeah. Can I interrupt with a quick question? What
Sure.
do you mean? What do you mean by probability of recovery?
Oh, sure. So, all right. So I didn't say it correctly. So we run this recovery process several times using different measurements. Basically, this depicts the fraction of times where our algorithms correctly recovered the underlying signal.
And it's exact recovery. So this is not approximation. You're running the.
Here it's exact. Yes, because the underlying signals are exactly k-sparse. Yeah, we also have experiments for approximate notion, but they are a bit more difficult to describe, right? Because you no longer can have this simple relation between the number of samples and probability, right? Because you also have the error.
Thanks.
Yeah. Yeah, so that's basically the performance of our algorithm, and in particular, you can see that our algorithm performs better than, say, COSAMP or Bayesian pursuit, which are algorithms which don't take structure into account, right? So, for example, here, right, you can see that if you don't take structure into account, you need this number of measurements, right, to get good probability of recovery, while here we get we can live with fewer number of measurements. So that's in terms of quality. Now in terms of time, these are timing experiments. And so this is a plot in the linear scale. This is in the logarithmic scale. So you can see that our algorithm runs, it's not the fastest algorithm of the lot, but it's certainly not the slowest, right? So this is the struct OMP, right? This algorithm does certain exhaustive enumeration, so it can take quite a lot of time. Our algorithm is roughly 20 times slower than the fastest algorithm of the lot, right? So this is the COSAMP, right? So it is order of magnitude slower than COSAMP, but at the same time, its quality of recovery is significantly better, right? Because you can see that we can recover. Our algorithm recovers from fewer measurements than this red curve here. So altogether, the conclusion of this experiment is that it's our algorithm provides a nice trade-off between the speed of recovery and the quality of recovery. Okay, so this is all that I had to say about the algorithms, or in fact, pretty much anything. So in the last few minutes, let me conclude. So what we have seen is an approximate algorithm for structure sparsity. So I defined what it means and what kind of algorithmic results one can get. And I will also show the application to compressive sensing, right? That we can use structure and get better measurement performance while having a reasonable running time. So if you are interested in learning more about the topic, Chin, Ludwig, and I recently wrote a survey that appeared in ethics bulletin. It's also available on our website. So this survey basically follows the structure of this talk, but it's more in depth. It contains a few more details of the algorithms. Now, there are lots of open questions that are left. And here are two examples. So one example, one question that is actually very, very interesting it comes from the following situation, right? So in our analysis, in particular, our analysis or the analysis done in the previous work, when we show that a small number of measurements suffices, we assume that the measurements are done using matrices with ID entries, like, for example, Gaussian matrices. Right? This is the only way we know how to prove that algorithms perform a good recovery from only k or order of k measurements. However, in practice, we and everybody else, we don't use these matrices because they're just too big, right? So instead, we use subsampled Fourier or Hadamard matrices, right? So basically, there's a disparity between what we use to prove things and what we use experimentally, right? So it would be very nice to close this disparity. Right now, for the general sparsity without any structure, it is known by the results of Candace and Tao that using these measurements, you can recover from, say, k polylog n measurements. Right, so there are beautiful results that basically shows that at least up to this polylog factors, this is a theoretically valid approach. But we don't have anything similar for the sparse models, in part because to get for the structured model, in part because there we really would like to show that we can get close to k. Right, so polylog n, it's we can get anyway, right? So we have to get something which is polylogarithmic in k, right? So in a sense, we have to show a gap which is smaller, which makes it harder. But it's a very interesting question. Another very interesting question is something that Thomas already alluded to. Can we prove any notion of hardness of some of those problems? And in particular, I would love to have some evidence that solving tree sparsity exactly actually requires k times n time. So there has been lots of results recently that shows that under some assumptions like strong exponential time hypothesis, certain problems which have a quadratic time dynamic programming solution likely cannot be improved any further, right? So I think it would be really nice to have such evidence for tree sparsity problem, right? But we thought about it a little bit, but it doesn't seem to be easy. So that's certainly a very interesting question. And there are many other questions, and we list them in the survey. All right, so that's it. Thanks for staying around, and I'll take any questions.
Thank you, Piotr. So, any questions? Maybe let me start. Oh, go ahead, Thomas.
Yeah, so there was one question about, again, the inapproximability now of the graph case where it's NP hard. So can you comment on that?
Oh, right. Yeah, I forgot about that problem. So, I mean, I would need to double check because some of the things are tricky, but I believe that the NP hardness of this problem, which comes from the reduction from Steiner tree, I believe the inapproximability also transferred by this reduction. So this means that whatever hardness you get for the Steiner tree problem, you also get for this problem. However, I'm not 100% sure, so it might be better for me to double check it, and then maybe I will clarify it in the final version of the slides that I can send it to you guys in a few hours.
Do you know the hardness of inapproximability for the Steiner tree problem? I don't right off the bat.
Right. So, so for Steiner tree, I don't know what the current best constant is. Yeah, I suspect it's something which is probably it's of the form 1.1 1 something, right? Or one point something, right? It's probably not very strong, but it's certainly known that Steiner tree is hard to approximate up to some constant factor, right? So whatever this constant factor is, I believe it should transfer to this problem. But again, let me double check it and then clarify it on the slides.
So Clement just linked to a paper which shows 96 over 95 in approximability, but we don't know if that's the curve.
Okay.
Maybe Piotr, maybe we can say a word or two about the how you managed to do the compressed sensing, just kind of roughly how it works. Typically, compressed sensing, you do it by solving this L1 minimization, but you have this extra oracle. How does it exactly fit in? Do you have to solve a convex optimization, or?
Oh, right. So yeah, it's a good point. I'm sorry I didn't get into detail about it because already as it is I went over time. The basic idea behind the fast algorithms for doing compressive sensing is instead of solving a convex optimization, at least instead of solving it directly, you use an iterative approach, right? So this algorithm by Needle and Trop uses a so-called iterative hard thresholding method, and the idea is that you basically find some approximation, and then you improve over this approximation, and then improve over this improvement. And you can prove that you converge to the good enough solution after logarithmic number of steps. This algorithm, as well as So basically, the main step in this algorithm is given some signal, which is not necessarily the original signal, but something that you recover. Given this signal, find the best k-sparse approximation to that signal. So that step is trivial for the general sparsity. But what these guys showed is that in the context of a structure sparsity, you can just replace that step by the model projection oracle. Right, so you basically iteratively keep improving your approximation by finding a k-sparse, structured k-sparse solution to whatever you currently have. Right, it's a bit more complicated, but that's the basic idea. Right, so that's how we that's the framework that we also use. Right, we basically use exactly the same framework. But we show that actually plugging in approximate model projection suffices, as long as you have both the head and tail approximation.
Any intuition for that? Why we need both?
The intuition for that, right. So you need that tail approximation at some point because your guarantee at the end is of the tail form. Right, and in particular, if the error is 0, then you want to recover things exactly. Right, so that's why you need tail.
Right.
Now, the reason why you need head is because at the very beginning, you might the signal that you want to find structure in, it's actually quite noisy. Right, so there is data there, there is information there, but there is lots of coefficients which are basically random. Right, so if you try to solve tail approximation there, then those random coefficients will actually dominate the tail, which would mean that tail guarantee becomes meaningless because it's so large that the tail approximation could as well just report 0.
Yeah, right.
Yeah, and that would still satisfy the guarantees, right? But you still want to make some progress. And it turns out that head guarantee is exactly what you need to make some progress, right? That if there are say 2 large coefficients, plus lots of noise, the head oracle has to at least report 1 large coefficient, right? So you at least make some progress in a meaningful way. Yeah, I'm not really doing justice to it, but that's the basic intuition.
Mm-hmm. Thanks. Any other questions? Okay, so I don't see any other questions. Let us go offline. Thank you again, Piotr, and hope to see everyone here in 2 weeks for Virginia's talk.
Thank you, guys.
You're welcome to stay here. We can ask more questions.
Oh, sorry. I had one last question. Sorry,
Okay.
the mic wasn't giving us trouble. The approximation algorithm you gave in the for the graph sparsity model. So that went. So maybe you said this, but this works for any graph. It's generic, like your model. The pictures are planar graphs. So if you were to assume that the graph has a bounded degree, or maybe it's a planar graph, or it's a grid to start with, can you get much better in these cases, or does it make sense to me?
Right. So definitely price collecting Steiner tree problem for planar graphs can be solved much faster and with better approximation. Well, not much faster because it's already pretty fast, right? But yes, there are some nice n polygon algorithms that have 1 plus epsilon approximation guarantee. So that there are pitases for this problem. I believe you could use them to get a better performance. We didn't try it though, because it turns out that for the application to compressive sensing, just having a constant approximation factor suffices, right? In fact, we don't really get much more improvement if we improve this constant, right? There's some low order terms that gets improved, but yeah, but it's not necessary to get this improvement. But yes, there are faster algorithms for the for this basic subroutine that we use, right? Price collecting Steiner problem. I believe it's a work of Phil Klein and his co-authors, right? There are some very good algorithms for that.
Thanks.
Sure.
Excuse me. Hi. I wonder, is that meaningful to ask the question like, can you get tail approximation and head approximation at the same time?
So that's a very good question, and for some reason we couldn't get it. I honestly don't know why. Somehow the tail approximation and head approximation, at least for tree sparsity, use somewhat different techniques. Right, so tree approximation, the tail approximation uses Lagrange relaxation. The head approximation uses greedy algorithm. So it would be nice to have one algorithm which has both properties and which is fast. I have no idea whether it can be done. It's a very interesting question.
Can't you just combine both, take the better of the two solutions?
Sure. Yeah. So yeah, I should be more specific, right? So sure. Yeah, you can combine. Yeah. I meant natural. Yes. So something that naturally leads to both guarantees.
Okay. Thank you.
Sure.
Any other questions? Piotr, you can get out of screen share, so at least you see us for a while.
Oh, yeah, that's a good point.
I think there are no other questions. So
cool.
Thank you, everyone, for joining us, and hope to see you in 2 weeks. So let's go offline, and everyone's welcome to stay and chat a bit longer.